Howdy, IB Math. It is Miss Kosh. I was realizing that I may have notes that cover all this, but I didn't exactly teach these notes in a video, so let me do that. This is kind of the beginning of how we do probability here. So, an impossible event has no chance of happening, and it is assigned the probability of 0. A certain event has, I don't know what I intended to go in that blank. A certain chance has a guaranteed chance of happening. A certain event has a guaranteed chance of happening, and it is assigned the probability of 1. So if it's guaranteed to happen, if it's definitely going to happen, there's no way it could not happen, it has a probability of 1. And so probability lives in the world between those two numbers. Okay, so experimental probability is a relative frequency of an outcome. So we look at this one. I may not actually give you the decimal approximations, but experimental probability is where we're working with a data set. So we don't have this theoretical situation. We gather data and kind of look from the data that we have and see what conclusions we can draw. Okay, so based on this, we're looking at different visitors to Australia. They have reasons for coming and how many people came. So it says estimate the probability. I'm going to omit the word estimate because I'm going to give you an exact value. I'm too lazy to find a calculator. Okay, so the probability the person who visits in June is on holiday. Well, notice here are all the people that visited in June, and some of them right here were on holiday. So it is this 156,500 people out of the total. This is not a reduced fraction. I'm too lazy to get a calculator. And that would be how you find the probability. Okay, and the next one, the probability that a person who came to Australia in the period April through June arrived in May. Well, so that means we have to take everybody that arrived in this world, in this interval, and make that, that's the total. We have to add all those together, this 3, 1, 2, can you see what I'm doing? And see, I think you can. 500 plus 260900 plus 308300. Hopefully I copied that down right. If not, the math idea is the same, or is correct. Okay, so that's how many people came to Australia from April to June, and they want to know what's the probability that the person arrived in May. Well, there were 260900 people that came in May. And so we would put this in our calculator and figure out what's happening. But I don't feel like it. Okay, and then it says, Lars arrived in Australia to visit his brother. Estimate the probability that he arrived in April. So what we want to look at is how many people came to visit family, because I think that's one of our choices. Visiting friends, relatives. So this world right here involves these 3 numbers. And then we want to figure out what's the probability that he came in April. Well, okay, so it's April was 77500 out of the total, so it'd be 77500 plus 52700. Oh, that's a 0. Plus, I did not give myself enough space, 59900. That looked terrible, but hopefully that makes sense to you. Okay, I had more. Now it says people exiting a new ride at a theme park were asked whether they liked or disliked the ride. The results are shown in this table. I found it helpful to figure out some totals here. So the total number of children was 72. Do I know how to add? That gets me 62 plus 10 more is 72. Okay, the total number of adults was 58. Then the total number who liked the ride, 30, that'd be 85, but it's 2 less than that, 83. Disliked the ride, this becomes 47. Add that together, 90 plus 40 is 130. And that works here also, 60, yes, 130. Okay, so find the probability that a person who randomly selected person likes the ride. Well, liked the ride, there were a total of 83 out of the 130 people. Now, IB wants either 3 sig figs or an exact value, and that is exact, and I'm too lazy to find a calculator. Is a child and disliked the ride. Okay, is a child, there were 72, but they could also be an adult who disliked the ride. Oh, no, ha, 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 I got that wrong. Today in class, I told everybody to stand up who was I first started with stand up if you were a boy I said stand up if you're a boy or wearing a blue shirt. And so all of the boys in my room and the girls that had a blue shirt on, all of those people stood up. So it was a lot of people. I can't really demonstrate this on the paper, but there were a lot of people that stood up. So that was boys or blue shirt. And I had and boys That would be something like, I could say boys union blue shirt. Okay, and this had a big group of people. And then I said, stand up if you're a boy and wearing blue shirt. So that's the intersection of those two worlds. And then I think I only had 3 boys today that happened to have a blue shirt on. Okay, so maybe I had 4 girls and a total of 7 boys in class or something like that. So I had like 11 people stand here. And on this one, it was a smaller group. They had to make both things true. Okay, so this one is saying find the probability it's a child and they disliked. So both of these things have to be true. They have to be a child and they have to have disliked the ride. So it's 17 out of the total group of 130. Is an adult or disliked the ride. This is that scenario where you have either you're an adult, which was 58 people, or you disliked the ride, which is an additional 17. So notice it's like these 3 things right there. 58 plus 17 is 75 of the 130. And then it says, then this last one changes the world we live in. It says disliked the ride given that the person was an adult. And we would say this, the probability they disliked the ride given, we draw a line for given that they were an adult. And this would be equal to, how many adults did we have? We had 58. And of those, 30 disliked the ride. And maybe I should reduce and maybe I should come up with a decimal, but I'm gonna move on. Okay, the sample space U, this is the universal set, and so it tells us what world are we living in. 2 events are complementary if, well, together they make up the universal set and no element in one is also in the other. Okay, so they're complementary. So the probability of A and the probability of the complement of A would equal 1. So in a Venn diagram, it's like you could either say, okay, here's A and then here's the complement of A. Or you could say, here's your universal set and this is A inside here, and so everything out here would be A prime, not A. Okay, can we read this next question? I hope so. It says a normal 6-sided die is rolled once. Let A be the event of the prime number. We were struggling today. Is 1 prime? I think it is. Okay, but the sample space U would be the set 1, 2, 3, 4, 5, 6. If you're rolling a dice, that's the set of values that you get. If you're looking for A, the prime numbers, I think 1 is prime. 4 is definitely not. 6 is not. Okay, and then what would be not prime would be the set 4 and 6. Draw a Venn diagram. Okay, so here are your A values. We had prime numbers were 1 and 2 and 3 and 5. And then out here somewhere is 4 and 6. Super. Okay. There's more. I hope you can kind of see what I'm looking at. They're printed kind of lightly. Okay. Illustrate a possible outcome when 2 coins are tossed using a 2-dimensional grid. Okay, so when you toss 2 coins, you could get a head or a tail on the first coin. You could get a head or a tail on the second coin. So this would be heads, heads. This would be heads, tails. This would be tails, heads. This would be tails, tails. Okay. Or a tree diagram. Well, what can happen the first time? We could get a heads or a tails. Then your second throw, you could get the head the first time, and then the second time you get a head or a tail. You get tails the first time, and then you could get a head or a tails here. And we use a lot of these in IB. They like those a lot. Okay, I think on this one, this was blue, this was blue, this was blue, and this was white. Okay, so they said draw a tree diagram to illustrate the possible outcomes when the spinner is spun 3 times. So the first time, we get a blue or a white. Oh. And then we could get a blue or a white for the second spin. So we could go blue, blue, then blue or blue, white, or we could go white, blue, white, white. And then we could get, from each of these, we could get a blue or a white. Okay, so I think, highlight the outcomes corresponding to the obtaining blue twice. Okay, so obtaining blue twice, I just found, I don't know, some weird marker. Okay, obtaining blue twice means I could go this, blue, blue, and then white, or blue, white, blue, or white, blue, blue, because white, white doesn't let me. So those 3 paths give us the outcome corresponding to obtaining blue twice. In class, we threw in some probabilities. Since we had 3 blues and 1 white, we knew the probability of blue was 3/4. I may have been jumping the gun. They may not have to do this yet, but then this is 3/4 and this is 1/4 and 3/4 and 1/4 and 1/4, 3/4. Can you see what I'm doing? I think you can. 3/4, 1/4. I don't know why I'm writing them in a disorganized way. But if I wanted to find the probability of getting exactly 2 blues, this way, this is 3/4 times 3/4 times 1/4 gives me 9/64. This path, 3 times 3/4 times 1/4 times 3/4 is also 9/64. This became 9/64 also. I think what I did is, what's the probability of getting at least 2 blues? And so then I threw in this one, the probability of getting exactly 3 blues, which was 27/64. So then we can add all those up, and that becomes, well, 9 plus 9 plus 9 is 27, plus another 27 is 54/64, which reduces, but I don't feel like it. Cool. I think that was the end of the notes for today. I'll make another video for the second part, but like, subscribe, comment, and go practice.